Hi there. Welcome back to another lecture in BCIT's Technology Teacher Education Structures class, TTED4044. If you're enrolled in the class, you're going to find some of the handouts for today's lesson on truss calculations and truss rules are going to be available on Desire to Learn, our learning webpage. And let me just flash over and make sure you can see where that's going to be. You'll find it all classified under week 3 triangles and trusses. And so you'll see those notes right in there. And if you're not enrolled in the course and you're watching this video, I hope you're enjoying it. Okay, let me just switch this screen back here. I'll just pop that into a small window right there. And let's get started here because the first thing I want to talk about is the handout that says truss rules and buckling on it. Now, the buckling I'm not going to get into too much today. We'll probably cover that in an upcoming lab. In fact, the year that I'm making this, 2021, we're going to cover it on Thursday's lab. But I did want to talk about truss rules before I start talking about manual calculation of trusses. So there are some rules that we have to follow and know about in order for our calculations to work. And the first one is the assumption that we're making for our trusses that all of the joints or nodes are pinned. Now, what do I mean by that? Well, when I say pinned, I mean that the joints are joined by something like where's that camera? Single screw, or in this case, a pop rivet. And so left to their own abilities, the joints would rotate like this. Now, they wouldn't twist or anything like that. There's just a pin going through right there. Now, in reality, not all trusses are made that way. Quite a few of them are gusseted right in here, and they're joined together, and there's a brace and welds going on so that this isn't truly free to rotate. But because the member is so long relative to the forces being applied, that member will actually twist up and down, um, effectively giving you something similar to a pin joint. In the event that your members are so stiff and rigid that they're not flexing like that, and you calculate your structures of truss, this is something that engineers actually like because you're making your calculations more conservative than they need to be. Because if you do have a rigidly fixed together structure where this can't rotate, that's just another brace that you have in there, and it makes the structure stronger. And engineers are always happy to do a calculation that comes out slightly weaker than the actual structure. Anyway, in order for a truss to be rigid, you need to get it into triangles. And so it needs to come together right like that. If I put one more pop rivet in right here, just throw this together right here, where that used to be a really flexible structure. Now you can see that it's a really rigid structure and there's no flex in any direction because we've built it into a triangle. Oh, nice camera angle. Anyway, so I think we've covered that before in a couple of other lessons, but when we're talking about our truss rules and I say all joints must be pinned, sometimes you'll hear me refer to the joints as nodes. That's what I'm talking about. Okay, and let me zoom in a little bit here more so that there we go. And we also have a rule that loads are only applied at the nodes. Okay, and that's because without the gusseting taking place in there. So if you've got, let's just do a simple truss, you'll notice that I've always given you your supports right at the nodes and your forces being applied right at the nodes or joints. And that's really important to how we calculate the truss, because if you start applying forces right in here, you then have to start getting into calculating beam buckling, okay, because that beam's going to want to start to bend in there, and then you'll have to resolve that force to say how much force is coming right here and how much force is coming right there. Now, obviously people can do that, okay, and if you go through and you're doing a degree in civil engineering or any kind of structural engineering, you're going to learn how to do that, and that's expected. But this is an introduction to some simple structures, so you can do some bridge building projects with your students, and we're just going to stick to the basics of trusses. So Joints are pinned, loads are applied at the nodes, also known as the joints. Okay, now we also, in order to do a manual calculation, get to use these big words right in here. The truss must be statically determinate, but not overconstrained. It's kind of like delightfully tacky yet unrefined, to use a probably out of date reference. But anyway, statically determinate, but not over constrained. You can take that home at the end of the day, and when your spouse, partner, friend, roommate, whoever says to you, "What'd you learn today?" Well, Jason had an interesting lecture on trusses, and we learned that they must be statically determinate, but not over constrained. And they'll sit there and say, "You got value for your tuition dollar today." Or they'll have sympathy. What do I mean by that? Well, there's this formula right here, okay, where 2 times the number of nodes has to equal the number of members plus the number of reaction forces. It's getting better all the time, isn't it? Okay, 2n equals m plus r. Well, let's take a look at what I mean by that by looking at a simple truss. Okay, so our nodes are these joints in the corner. So each place you put a pin in counts as a node. So right on here, I see 1, 2, 3 nodes. So here I've got n equals 3. And then I've got members. Now the members are what join the nodes together. Let me grab another pen here. So our members are right in here. There's 1 member, 2 member, and 3 members. Okay, so our members equals 3. And our reaction forces, well, right in here, we've got 1 reaction force coming up from the ground. Okay, it's lifting up that way. Here we've got another reaction force coming up from the ground, holding it secure that way. And here we've got an external force being applied, and that is our load. So our number of reaction forces equals 3. So when I take that and I say 2n, okay, 2 times 3 is 6, equals 3 plus 3. So although the words are really big, the math is really small. Okay, 2 times 3 equals 3 plus 3. That means we can calculate it as a truss. Okay, we can calculate it manually. There's a whole bunch of computer calculations and more sophisticated calculations and even manual calculations that people did long before computers came along that can be used to solve trusses that are either statically indeterminate or over-constrained. Actually, the statically indeterminate ones are pretty hard to solve because they tend to collapse and they don't actually work. So what we mean by statically determinate means it has to be capable of standing up. You can't have floppy joints that aren't braced and that are going to fall apart. Okay, so we'll take a look at some indeterminate and some overconstrained situations down below here. Okay, so let's take a look at this one right here. And this truss right here has reaction forces right in here. So we'd have that one hooked up to ground, that one resting on the rollers, and we'd have a force applied right there. So when I do my counting, I'm going to come along and say, well, I've got 4 nodes, 1, 2, 3, 4. I've got 5 members, 1, 2, 3, 4, 5 members. So 2 times my number of nodes is 8, so 2 times 4 is 8. Equals 5 plus 3. So this structure is statically determinate and not over-constrained. So we can calculate this, and we can go through and we can calculate how it's all going to work out. Now in this case, the solution's really kind of trivial, and all of this force just goes straight down into that line right there, and it's kind of boring. But this leads into something called zero force members, which are necessary for this to not topple over to either side. But when doing manual calculation, these ones would show up as carrying zero force. They're critical to the structure, but if everything is perfectly aligned and perfectly set up, they carry no force. They're just there case the wind blows and this moves a little bit right there. It just keeps this thing from toppling over that way. Now, consider this example right over here where we've got an extra member added in. So this is the same thing, but we've added another member right across here. Okay, well, now we've got a problem. Now, it makes the truss stronger. Believe me, this will stand up. This is still statically determinate. In other words, it's not going to collapse. It's not going to flex or fold. Okay, but the problem for doing our manual calculations now is because we've got this force coming down right here, we're going to have a hard time resolving how much of that force comes down this way and how much of that force comes down that way. And it's not that it can't be solved. It can be solved, but not by the method I'm showing you today. And you don't know how to have to know how to solve that type of problem in this course. So when we're talking about statically determinate, we mean a truss that'll stand up. When we talk about overconstrained, this is what we're talking about. You've got more members than you need, or more braces to support that load than you absolutely need to support that. Now down here we run into a truss that is not statically determinate. Okay, so if you take a look at this one right here, count up the number of nodes, and we've got 1, 2, 3, 4, 1, 2, 3, 4, 5 nodes. Okay, and you can already see that it's not going to stand up. Like this triangle's great. There's 3 members right there, and there's 3 members right there. Okay, so there's 6 members. Members equals 6, and then our reaction forces, we've got a little triangle right in here, little triangle right in there, and an applied load right up there. So that's 1, 2, and 3. Okay, so our external forces acting on it, our reaction forces on the structure, are going to be equal to 3. And so 2 times n equals 10, but our members plus our nodes only equals 9. And so we don't have enough members to support that. And obviously, if you look at that, you can see if that force acts right there and all the joints are pinned, this is going to start rotating in this way. Okay, and this will start rotating in this way as this node goes down right here, and the whole structure is just going to collapse down like that. So that's going to be a problem with calculating that structure, because there's really no way to calculate the forces in a structure that won't stand up. Well, not using statics. As soon as things start moving, it becomes dynamics and kinematics and other interesting fields of physics that we're not getting into today. Okay, so anyway, obviously to fix this, because you need to make your equation be true, 2 times n equals members plus node. So we need to get these two numbers to add up to 10. Now, you could say, oh, well, we'll just pop another node in there. But if I pop another node in right there, well, now the number of members is increased as well. And we've got a problem again. Or sorry, we could put another reaction force in. You could put a reaction force in right here, and you could lock this node in place. Well, now that can't rotate, and you're good. Or and you're looking at this saying, do it the easy way, Jason. Just put an extra member right in there. And that brings you up to 7 members. So 7 plus 3 equals 2 times 5. The math's not that hard. Sometimes applying it to these situations can be a little bit tricky. How about this one down on the bottom? After you do the trusses for a while, and after you look at them and understand internally, after you've internalized what we're going for, you can look at that truss and say, yeah, I can calculate that one. But if you're not 100% sure, just say, well, there's reaction forces. And it doesn't matter whether my load is being applied right here and I've got something pushing up on that structure and these 2 nodes are secured, okay, or whether I've got the load here and these 2 are secured. It doesn't really matter which one. The most common one in this situation would be that node would be secured, and this node would be secured, and we'd have a force acting out right there. Okay, we've got 1, 2, 3, 4, 5, 6 nodes equals 6 members. No, Helps if I color them as I go. That way I don't lose track and forget which ones I've counted. 1, 2, 3, 4, 5, 6, 7, 8, 9. Members equals 9. And reaction forces equals 3. 2 times 6 equals 9 plus 3. All comes out to 12, and we're good. Okay, so I'm generally, when I give you quizzes, going to give you trusses that you can solve. But you should know that the techniques that we're showing you right now apply to a subset of structures, okay, known as the statically determinate trusses that are not overconstrained. It's a section of the world that it's limited, but by looking at the limited section of the world, we can learn some rules that will help us understand a more complex section of the world, because everything we learn in here can be applied to the next level of calculation. This is kind of like your entry level to learning how structures work. So here's more examples on the rest of that handout, and we talk about fully constrained trusses. And if it's still making your head spin, go ahead and take a look at this, and you can go through, and here's some more examples of trusses that are fully constrained, over-constrained, and under-constrained. Oh, right, I zoomed in. I need to move the page up there. Anyway, on the second page of this handout, you'll find some more examples to take a look at, and hopefully that's kind of making sense at this point. So I'm going to spend some time now talking about these properly constrained trusses. Now, also in this handout, I have information on buckling, and I'm not going to include it in this lecture, because in our next lab, we're going to take some members and we're going to squeeze them. Was that pre-meme thing? I'm shrinking your head. Saturday Night Live thing from the 80s. Wasn't that funny then either. But anyway, how did I even get on that topic? We're going to take a look at doing compressive forces and talking about how compressive forces work. And you've probably already had a little bit of experience looking at them from using the Bridge Designer software and noticing that members behave quite differently in compression than they do in tension. So you can just put aside the rest of that handout until your next lab session, because we'll be covering that in more detail. Where we are going today is we are going to dig in to the truss calculations for a larger, more complex truss. And I recommend that you grab a beverage, perhaps caffeinated, because this does take a little while, and there are intricate, detailed steps that hopefully are laid out well in this handout. And it's a general set of rules that, if you follow through with them, can help you with solving pretty much any statically determinate truss that's not overconstrained. There is. Sorry about that microphone right there. So let's get started here. Our analysis is going to be exactly the same as we were using on our simple trusses. So if this was a single triangle and the structure came right up like this, okay, and we just had one member across the bottom and it was just a single triangle right in here. Hey, look, I've got a single triangle truss, just the right size to demonstrate that. If that's what we had, you'd know that what we'd have to do is we'd have to say, well, we've got a force at this node right up here, and we've got restraints right down here. We need to balance the force at the restraints, calculate our reaction forces by neutralizing the moments. And this applies to any truss that you're looking at. Okay, so in here, what I'm going to do is, you'll notice that the load right here is not applied directly at the middle. It's kind of skewed off to one side, just like in last week's lab. Just zoom out a little bit here to get a slightly bigger picture. And so what we're looking at is we want to balance force reaction A and force reaction C right here. So we're looking at nodes C and A right now, And we're trying to come up with the force out here and the force right here that will keep this force right here from making the whole thing spin this way, okay? Because given no other forces, this force is going to act down right through here at this lever arm. And this lever arm is acting at a distance of 3 meters, okay? And it's got a force of 1,000 newtons coming down right there. So here's our F load times 3 meters, okay, is going to be 1,000 times 3, and that's acting right in there. That's our 1,000 newtons comes down here at a right angle, and we just say 1,000 newtons times 3 meters is what's making this truss want to spin that way. So to counteract that, the only other place where a force can be applied is right out here at point C, okay? And that is acting at a distance of 6 plus 6, so that's acting at a distance of 12, okay? And that's our force reaction C right there. So our formula, when we write it out, F load acting at 3 meters is counteracted by F reaction C times 12 meters. And if those two have to equal out to 0, well, we do a little bit of algebra in here, and we can say that F reaction C, if we divide both sides by 12, is 1,000 newtons times 3 meters divided by 12 meters, comes out to 250 newtons. Now, one of the neat things about doing all these calculations is if you keep your track of your units, okay, the units will cancel out. And sometimes you can solve a problem by, if you forget the formula or the next step, you say, well, I've got newtons and meters up here and meters down here. What have I got to do? I've got to do a divide. So, because I need to get an answer in newtons. So I want these 2 meters to cancel out, and meter divided by meter cancels out. Okay, so right in here, all those algebra rules apply to units as well. It's really cool. One of the beauties of the metric system, in fact. Yeah, imperial system does it too, but meh, imperial. 250 newtons is going to be our answer. So F reaction C, pushing up right in here, is going to equal 250 newtons. All right, now, if I've got 250 newtons pushing up right here, and 1,000 newtons pushing down right here, then if I want to keep this thing from moving up and down, then my reaction forces, F reaction A and F reaction C, have to sum together to counteract the 1,000 newtons pushing down right here. So I can come along here and say the sum of the forces on the truss have to equal 0 as well, so it's not accelerating everywhere. And so my F load minus F reaction A plus F reaction C has to equal out to 0. And again, a little bit of algebra, and I know that F reaction A over here has to equal 1,000 newtons minus 250 newtons. So I get 750 acting up right in here. Okay, we've done that a couple of times, and right down here, we sum this up and we describe our forces, 750 newtons acting up right here upwards, 250 acting down. Now, do a reality check when you're doing this. Picture this as a couch, your person A, your buddy's person C, and your useless buddy D comes along and hops on the couch right next to you. You carry more load than buddy C down here because the load is closer to you. If it worked out the other way around, maybe you did the numbers right, but just put the forces in the wrong place, and that can be a little bit of a problem too. Okay, so let's take a look right on here. If you chose, instead of doing your moments about point A and saying I want to keep it from spinning that way, you could perfectly equally do them about point C to prevent it from spinning that way. Okay. The results would come out exactly the same. Feel free to go ahead and try it, because what you'd be having right here is you'd have 6 meters plus 3 meters. You'd have 1,000 newtons times 9 meters divided by 12, and it would come out to 750 acting up at point A. And then you could come back and say, well, 1000 minus 750 leaves me 250 acting up at point C. Okay, so it does work out really nicely. And as a general rule, you can apply this to any structure. So if instead of this being a truss, okay, it was just some kind of blob that came right through there and had those forces applied at those points, in order for it to remain static, so that we could do a statics calculation on it, that blob would have to stay in place. We're going to apply the same concepts to the individual nodes here in just a minute. So hopefully page 1 is stuff that you've already done before, and you fast forward through a lot of this because you know what I'm talking about. Okay, now we're going to get into step 2, and this should also look familiar to you because we've done this for single triangles. Okay, and pardon me for just a second. All right, so now what we're going to do, and you can start at either end, but I like to start at the end that is close to where the load is being applied. Okay, because that, I think, gets us to our answer a little bit faster because we can start canceling things out a little bit sooner. So if the load was applied down at this end at point E, I'd probably start doing this calculation from the point C side. And if the load was being applied at point B, I wouldn't worry too much about it because that's right in the middle, and I'd have equal forces coming up on equal sides, and the whole thing would be in symmetry, so I'd actually save a whole bunch of calculations. Okay, let's go right in here, and F load equals 1,000 newtons coming down here. A's got force coming up right here. Now we know that there is 750 newtons of force acting vertically right in here. Okay, now that 750 newtons that's pushing up on point A has to push up on this member right here. AB can't support any vertical force because there's no vertical component to that member. That member is purely horizontal. Okay, and if you push up on this end, it would just rotate on its own. Okay, but because there is vertical component to AD, then that one can support vertical force. And that vertical force, that 750 newtons, is going to be the vertical component of vector AD. Okay, so AD is the overall vector which runs along the hypotenuse of this triangle. And notice that we are using this triangle right in here. Okay, so just like we did in our lab, we have to break this down and take a look at this triangle. And we've got ADY right in here is going to equal F reaction A, which is going to be 750 newtons. Okay, now our similar triangle for this, using the sides and the length of the sides, we've got a dimension of 3 meters right down here because this is halfway along this 6-meter segment. And we gave you the dimension of 5 right up here. Okay, which means that when you do your square roots and everything, you come up with my favorite triangle, the 3, 4, 5 triangle. Sometimes I get really sneaky and I give you a 6, 8, 10 triangle. But it's a 3, 4, 5 triangle right in here. And, you just do Pythagoras to confirm that. And not every triangle I can give you can finish up that easily, but some will. And we've got a 3, 4, 5 triangle. So what we know is that our AD acts in the 4-meter direction. That's the vertical direction right in there. So I can come in here and I can say that my ADY force is proportional to the 4-meter direction, this side right in there, okay? So ADY, AD vector Y component right in there equals 4. And, well, proportional actually gets a little squiggly equally sign. And I can say that my AD vector, okay, is proportional to 5 meters right here. And my ADX is proportional to the 3-meter direction. right down here. And so we write that out, ADY over 4 equals AD over 5 and ADX over 3. Okay, now that lets us do some calculations down here. And so we do our first one. We know what ADY is. That's the 750 newtons, the vertical component right there. We divide that by 4. And then we can just multiply the resultant by 5 and by 3 to get these numbers in here. So after you've done the math and punch it all into your calculator as you're following along playing the home game, you should get some numbers that come out like this. And AD should be 937.5 newtons, ADX 562.5, and of course you don't have to calculate anything because we already knew what ADY was coming into this calculation. That should be similar to things that we've done before. Okay, so if it seems redundant and you're fast forwarding through it, that's a good sign that you've been following along, you're up to speed, and things are going along. If you're reviewing it, that's a good sign that I'm going along at an appropriate pace. Now, step 3 is where we do something slightly different. We've done this for a single triangle, which was been a little bit more simple. But when you move over to step 3, we call this nodes in space. And the instructor who was teaching this course when I came through the program, Phil Esworthy, he always made reference to pigs in space. So he would always pronounce this, we do nodes in space. And the Muppets have been off the air for a while. I hear they're coming back on Disney Prime. They're actually pretty funny. Anyways, yeah, Phil would always reference this as nodes in space. So anytime you look at this, we've got our nodes floating around in space. And here is node D. So node D, as you'll recall, is this node right up here that the force is being applied to. And we've got some members coming into node D right here, okay? D is connected in 3 different places. It's connected to A, it's connected to B, and it's connected to E, and it has a force applied to it. So we need to take a look at what's going on at node D. Now, just as we were able to say that the sum of moments and the sum of forces on our entire structure have to equal up to 0, the sum of forces and the sum of moments on any node within the structure also have to equal to 0. Okay, so if I just draw a little picture of node D, then all of the vectors coming in there have to add up to 0. Now the neat thing is, and remember I was talking earlier about how the joints are all pinned and able to pivot right about on here. Because these are pin joints, we don't actually have to calculate any of the moments acting right there, because if there was a moment, it would just twist like that. Okay, so we've simplified our equation massively by those little rules we talked about earlier on. And like I say, if you do build a structure where it's not perfectly pinned in there and that corner is stuck together, you've just made it a little bit stronger than your calculations, which is okay too. There are more sophisticated ways to do the calculation for that. We're not going there in this course. So this is flexible around here. We don't have to calculate the moments. We just need to balance off the forces. So we know that we have F load of 1,000 newtons. That was defined as part of the problem. We know that we have this member AD coming up right in here. Now I've drawn it in as a dotted line because that's where the real physical member is. But we've done some math on that real physical member and we've broken it down into 2 components. And this is why components are so useful, okay? Because we've got ADY that we know is coming up in here, and that's acting upwards. And we've got ADX, okay, which is pushing over on here, okay, because this is pushing at an angle coming through here. So part of that's pushing up and part of it's pushing over. So this side right in here is all what's coming up from AD, okay? Now, we've got some unknowns on there. We don't know what DE is, that member at the top that's coming over from there, or what this member coming up from B is. We don't know what's going on with them. Well, these equations are going to help us figure that out. So let's take a look at what's going on here. I'm going to start by summing the vertical forces, because since we've made components, we can do the vertical forces first and then the horizontal components second. Okay, so what we've got in here is, let's just look at our y components, and you can see that there's only three things acting in a vertical direction on this node. Okay, we've got ADY, which we already know is 750 newtons. We've got the force of the load, which is 1,000 newtons. And we've got BDY, which we don't know unless we do the incredibly sophisticated calculation of saying, well, if they've all got to equal 0, 1,000 minus 750 has to equal 250 newtons. So BDY has to be 1,000 minus ADY. Okay, so this number here has to add up to this number here to balance off against this number here. It's not so different from what we've already done, and that tells us what BDY is. Critical step in the next step that we're going to go on to. So BDY is going to be 250 newtons. Now, step number 4. Okay, we use BDY at 250 newtons to calculate BD and BDX, just like we did on the previous half of the triangle. Now, I'm going through this step by step and going pretty slow because you're looking at it for the first time. Believe me, it gets faster the 100th time that you've done it. It gets even faster when you have a computer do it for you. But it's important that you understand how all of the forces are canceling out against each other and pushing on each other, because that helps you understand why the forces are flowing the way they are. And when you look at your bridge designer truss, you might look at it in a new light and say, oh, that's why that one's in tension and that one's in compression. Keeping in mind that Bridge Designer actually had a slightly more sophisticated loading structure because it included the weight of the bridge, which we're not including in our analysis right here. So use BDY at 250 newtons to calculate BD and BDX. Same calculations that we do before. We've got our similar triangle over here, a 3, 4, 5 triangle, because we know it's 5 meters on there and 3 meters down at the bottom, and Pythagoras tells us that that must be 4 meters. And then over here, we know that the force of BD pushing upwards had to equal 250 newtons because we just calculated what BD's Y component was going to be. And now we can use our proportions and ratios to calculate what our total BD value is going to be and our horizontal component BDX is going to be. Okay, so now we can go back to that node D and we can start putting some of these numbers into there. So we started off with this low member coming up in here, and we knew that this was going to be 750 newtons, 562 newtons horizontal, because we'd already calculated that for right down here. We carried that over to here. This, plus the force being applied right here, allowed me to calculate that we had 250 newtons pushing up from this member coming in this way. The ratios and proportions based on that 250 newtons tell me that I've got 187 pushing sideways because of this vector right here. Okay, and now this allows us to solve our second member in this node. Actually, I guess our third, really. We're almost halfway done. And that allows us to take a look at DE, this member that sits coming right across the top at the top of the truss. And just as we added up all the forces on node D so that the vertical forces would balance out, now we can add it up so that the horizontal forces balance out. Well, I've got 3 horizontal forces coming in here. I knew this one based on what was happening down at node A, and I knew this one based on the ratios and proportions that were based upon the vertical component of member BD. And so here's my formula right here. all of the x components, okay, and DE is only an x component because it's perfectly horizontal. If it wasn't perfectly horizontal, we'd have a little bit more calculation to do, but we could do it. I won't make you solve that one, but certainly it could be done. And 562 minus 187 leaves the force remaining in that horizontal member, 375 newtons. So now we know all the forces acting at node D. They all add to zero. All that work, and we got nothing. If you got nothing, you did it right. Seems like a long time to go through to get nothing, but look at this. So now where are we? We're well on our way to solving this truss. Okay, we know the load in member AD right down here. We've calculated that out. That was one of our earlier steps. We know all the forces acting at node D, and we've balanced them out, which has informed us on the load acting in BD, and it's informed us of the load acting in DE. Okay, now keep in mind this one's pushing this way, so it's good to say whether they're in tension or in compression. Well, if E is pushing that way on D, this member is going to be in compression. A is pushing up on D, that's going to be in compression. B is pushing up on there, that's going to be in compression as well. So you can start going through and doing some calculations on there. Okay, we also know our reaction forces right down here. So this is going along pretty well. Okay, and just some notes down here on the bottom about thinking about tension and compression going on in there. And this is just a summary page. There's actually no new calculations on there, just a chance to go, okay, we're getting somewhere. Enjoy it for a second because it doesn't last. All right, truss calculation step number 5 on the next page. Okay, now if the geometry is very similar, then you're going to see a lot of the same numbers popping up. And to keep your life easy, I do tend to give you similar geometry across the truss. I've got 1 or 2 practice problems that are a little more complex. For those of you for whom this is making perfect sense and you want to challenge yourself, you'll have a chance to go ahead and do that. But if you're sitting there going, okay, thump, 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 brain expanding, then don't panic. That's a good place to be. All right. So step number 5. Now, you could do this step earlier in the process. So if you wanted to start with this process or do it, at any point you could, but let's go ahead and do it now. And we're going to jump over to node C. So remember node C was sitting way out on this side. Okay. Um, I don't have to jump over there. I know a little bit about what's going on at node B. I could have gone to node B next. I find it's generally easier to come over here because it's a little simpler calculation. We know what's going on pushing up that way. Okay, so we know that force reaction C was 250 newtons. Remember, we calculated that on the very first step. Okay, and since BC, the member running across the bottom right down there, okay, is horizontal, it can't support any vertical load. So we're going to apply none of that load on there. All 250 newtons are being expressed through CE in the Y or vertical direction. So CEY is going to equal 250 newtons. And you're probably recognizing a pattern right here. Look at that. I've done Pythagoras on this 3, 4, 5 triangle for the 3rd time today. 4th time? Okay, it's getting a little bit boring. If you have different shapes, if I give you a tricky one where the triangles aren't all similar to each other, if you have some different shapes in your truss, then of course this would be a different calculation each time and different ratio of vectors, but the rules and the steps and the process would be exactly the same. Okay, so CEY is 250 newtons pushing up on point E. So we're going to calculate the overall force in that vector and the horizontal force in that vector. And notice this time, because CE is pointed in this direction, the horizontal force is going to be going in that direction. So when it combines to the vertical, it comes up acting in this direction. Okay, so here we go, and we do our ratios down here, our CEY, which we know is 250. Okay, so that's 250 newtons over 4 meters equals what's going to come out to be 312 newtons over 5 meters, and CEX over 3 meters. Okay, so now we've broken that vector down, we've resolved it into its components, and this looks a lot like step number 4. Exactly, I was just saying if you had a truss that looked something like this with different geometry on each triangle, the steps would be the same, but the numbers would be different. Okay, so this kind of repeats some stuff that we've done before, and you start, after you do this for a while, to see a bit of pattern recognition, and that's a good thing. So, step 6, okay, nodes in space for node E. Okay, so up here at node E, we've got member C pushing up this way, and we've resolved member C into its vertical component and its horizontal component. Okay. Now, we know that all the forces on node E have to balance out. Well, don't forget we've got a force coming across on the top because we calculated that node D right over here, okay, is in compression or pushing this way so that node D could be balanced right in there. So we've got vector DE. If this member is pushing with 375 on that node, it's got to be pushing in the opposite direction with 375 on this node over here. Okay, so if that's happening right here, we've got 3 horizontal forces, and we've only got 2 vertical forces. You remember in the other one we had a third vertical force, which was the force of the load. So this makes our vertical forces trivial to calculate. So let's do them first. Let's take care of the easy stuff right on here. So if this one's pushing up with 250 newtons on this node, then this one has to be pulling down with 250 newtons on that node. Okay, because if this one's not pulling down and this one's just pushing up, this is just going to start accelerating off the page, which may be where you wish it would go right now. Okay, so this is coming down right in here. So this is going to be the first member that we've calculated that has a tensile force in it. This member's been in compression, this one's been in compression, but this one is in tension because B is actually pulling down on E because C is pushing up on E and there's no vertical constraint to stop that from happening. Okay, so vertical forces are easy. Horizontal forces are almost as easy right in here. Okay, we know that if we've got 375 from this top member coming over from D, being in compression and pushing that way, and the horizontal component of C is pushing over with 187.5, that our horizontal component right down in here is that if EB is pulling down this way, its horizontal component, EBX, is going to have to equal 375 minus 187.5, which means that 375 minus 187.5 means it's pulling with 187.5 newtons to the left. So this member in here in tension, whoops, pull that down. This member in here in tension is pulling down this way, which means it's pulling down like that and pulling over like that in its horizontal components, which kind of makes sense. If there's a string right here, that member E would be pulling that way. So this is pushing right up in here, and this is pulling, and those two pushing and pulling forces acting on E are exactly equal to the force that D is pushing over here. And if it seems like a miracle that they've canceled out, it's not. It's a requirement. Okay? Everything will work out and resolve, and all the sums of our forces have to equal 0 for this structure to stay in one place. Okay, and so now we've calculated member EB, our first tensile member, with a load of 312.5 newtons in tension. Okay, now if that 312.5 number is showing up a lot in here, that is because the structure has equally shaped triangles. A little simplification to keep life a bit easier. Okay, so we're almost there now. Look at how far we've come. Okay, we just need to calculate the stress in the bottom two members. We've got these two members down here. We've calculated here. That was where we started. And then we did this one. Then we did that one. Then we did this one. And then we did that one. And now we're just left with what's happening at the bottom. And to do that, we come over to node B and take a look at what's happening right in there. Okay, now, can also take a look at node C, I guess. Node C is probably a better place to start because that's what my notes say. But we are going to look at node B. I'm just getting one step ahead of myself. I'm excited about this solution coming together. Okay, so start doing some nodes in space to node C. Here's node C sitting right down here. And we've balanced out F reaction C with the vertical force. And since there was a compressive force pushing up this way with a horizontal component of 187.5, that means that this is also pushing down this way, okay? Because keep in mind, if this node is being held up by node C, then node E is pushing down on node C as well, okay? And that's what balances out the 250 newtons of reaction force in there. Okay, so that's coming down right in there. And when it comes down that way, it's got a horizontal component. And we've already calculated that horizontal component to be 187.5. When we were looking at the forces in that member, we resolved them up here. It was pushing this way with 187.5 and up with 250. That means down here, it's pushing this way with 187.5 and down with 250. So at C, if there is a force pushing that way with 187.5 newtons, then the tendency would be for C to swing out that way. But it doesn't, because over here we've got node B tied in place, and we've got a tensile member right here pulling on node C, so it doesn't swing out to the side. And since we've only got one horizontal force coming in here, the opposing horizontal force is really easy to calculate because 187.5 that way requires 187.5 that way to stop it. So we're going to have 187.5 newtons acting in member BC down there. And because it's perfectly flat, that's entirely a horizontal component. We don't have to do any vertical components or anything like that. We could do it if we had to, if this was some unusual shape, and if this node was sitting out in here and this member came back in there, we could do it, but we're not going to. All right, so let's move on. We are now up to Truss calculation, step number 3,456,500 and, yes. Okay, well, like I say, after you've done this a few times, it starts to become really automatic, becomes pretty simple, and you just go through and it all makes sense. Okay, so you do your nodes in space on node B right at the middle. Okay, now node B is one of the more interesting ones for doing your final nodes in space calculation because this is the last one that you have to do, and it has the most members attached to it. You've got 4 members coming in right here, which should make it the most complex. But because you've gone through and done all your calculations, it actually makes it one of the most simple because we know a lot of these numbers. Now, we've calculated the vertical and horizontal components in dB. So we've got dBy and dBx from one of our earlier calculations. We've got BEY and BEX from an earlier calculation. And we also just calculated BC, okay, from the calculation that we just did. Now, if you've done everything right, okay, you'll notice that you've only got 2 vertical components coming in here. And those two vertical components are equal to each other, but in opposite directions. Remember, this member's in tension, so E is pulling upwards on B, and this member's in compression, so D is pushing downwards on B right in here. So this is pushing down, and the only way that B doesn't swing out of the way is because E is pulling it back up. Okay. Now, as we've got those forces coming in right there, we also know that because this one right here is a pulling force, it's in tension, that we're pulling up that way, but we're also pulling over that way. Okay, so now we've got E pulling over with 187.5, C pulling over this way with 187.5. We just calculated that because B has to pull on C to keep C from swinging out of the way. And then we've got D pushing down this way and also pushing over with 187.5. So to keep B from swinging over that way, which it really, really wants to do based on what these three are doing, our A must be pulling it back in this direction with a force equal to 187.5 plus 187.5 plus 187.5, which is 562.5 newtons. Okay, and that is going to be your tensile stress in AB. And if you go back and confirm to make you sure you did it right, go back to step 2 and remember when we calculated ADX, okay, and we said that pushing up this way on D, A was pushing up with 750 newtons and over with 562. Well, that means D is pushing down on A with 750 newtons and over with 562. And when you go through and you calculate it all out, B is pulling that way with 562, canceling the horizontal forces at point A and locking point A in place. We have a statically determinate, not overconstrained truss that looks something like this. Okay, so we have some members that are in compression. So AD is in compression. It pushes up that way, and D pushes down that way on A. Okay. Now, because this isn't quite enough force to hold everything up in there, we had to calculate that this is also in compression right in here because it helps push up that way to help support the force of that load. Okay. Since this force, okay, is pushing over that way harder than this one's pushing over that way, there's some remaining force pushing over this way. So those members are all in compression. That was stuff that we calculated out fairly early on in the process. Then we jumped over to node C and we said, well, node C's got a reaction force pushing up on it. So node C has to be pushing up. So node C has to be in compression right there. Then we said, well, node C is exerting a vertical force on E, and because DE is perfectly horizontal, it can't fight any vertical force that's acting right there. So we must have this member in tension. Okay, so that one has to be pulling in like that. It's being stretched. And so if E is being pulled down to counteract the force that's in there, well, that means that E is pulling up on B, which counteracts the force that D is pushing down on B with. Okay, now down at the bottom, if we didn't have node B right here, the whole structure would swing out that way, and this would start to collapse. So in here, we have to have this member in tension, okay? And when we look at that, we've got at B, we've got this tensile member pulling that way. We've got E that tensile member pulling that way, and this compressive member pushing that way. So this one is in even greater tension. In fact, our greatest tension of the entire structure, 562 newtons, which very conveniently is equal to the horizontal force, the horizontal component of member AD. Everything balances out, and we got there in exactly 1 hour. I was aiming for 1 hour, but I wasn't expecting 1 hour and 14 seconds. Closer timing. I may have given this lecture once or twice before, but this is the first time I've recorded it, or timed it for that matter. So here's one that you can try, okay? We've got a load acting right here of 14,400 newtons. You'll find some of these numbers have been chosen to make sense. If you come down right here to get started, 16 meters, so this is halfway from there to there. I try to draw these to scale, so if you're not quite sure and you want to double check, you can take that out, and it looks like that. It didn't quite print to scale, but well, it printed to scale, just not a one-to-one scale. Usually I try to keep the scales pretty simple, but you can go through there and you should be able to tell that that's going to be 8 in there, and do your Pythagoras on there, and this should follow step by step. You can go back to step 1 and just put some different numbers in there, and you should come up with an answer. And when you do come up with that answer, you'll be able to go on to D2L and take a look in there. And okay, I'm working with single screen here, so I have a hard time scrolling through all this. But in that triangles and trusses, a little bit lower on the page, you should be able to find a solution for this problem, as well as a few other trusses that you can try. I'm also going to talk about how to solve some of these trusses using computer techniques, but I do expect you to know how to use the manual techniques. Okay, the manual techniques need to be in here, not because you're going to do the math calculations all the time, but because you do need to be able to visualize how those stresses are acting in there, so that when you punch something into a computer and it comes out garbage, you can look at it and say, oh, that's why, and troubleshoot the problem. Okay, if you don't have a visualization of how the forces are acting at each of those nodes, and why some members are in tension and why some members are in compression, then you're going to start running into problems. Alrighty, so have fun with that, and I hope that made the complex truss seem not quite so complex. Like I say, there's some solutions up on D2L, and I'm also going to talk about some computer methods for solving these as well. Then we're going to do a truss design challenge so that you can put this to use for real. All right, have a good afternoon.